This tutorial video is going to be talking about ionic bonding using transition metals. We had originally talked about ionic bonding not using transition metals, but now we're going to add a new layer and discuss how transition metals bond a little bit differently, or at least we write it a little bit differently to the traditional ionic binary bonds. So we need to first start by discussing and reviewing what are transition metals. And as a reminder, here's the periodic table that you are all familiar with. And you'll remember that there are certain regions and certain metals that are highly predictable. So we know that these alkali metals will always have a +1 charge. That's because they have one valence electron and are more likely to lose that one electron rather than gain 7. The alkali earth metals have a +2 charge. This column here has a +3 charge. This has a plus or -4 charge. We're not going to be working with these all too often. The nitrogen group over here has a -3 charge. Oxygen groups has a -2, and the halogens have a -1. And just a reminder, these noble gases have no charge because they have a full valence shell. So that brings about this central region over here that is very unique, and we call these the transition metals. And there's a reason we call this region the transition metals, and that's because they transition from how many valence electrons they want to show. And it all depends on the region that you actually find these metals from. Certain areas in the world will have coppers where it's just one valence electron that will be exposed. There's other regions in the world where it's 2 valence electrons that are exposed. So they are actually highly unpredictable. And they have a tendency to kind of tuck in some of their electrons so that they can actually be very flexible in how many valence electrons they show. And so what we actually do is we call these transition metals, and we need to somehow denote how we're going to identify those metals that actually have how many valence electrons they actually have. And I'm going to sort of make this transition region be a little bit bigger than what we've been talking about originally. And you are welcome to mark that on your periodic table. Everything within that blue region has a tendency to have multiple types of multiple types of charges. I'll go ahead and give you an example. So for example, we have iron, and you'll notice that I have iron with a Roman numeral of 4 and iron with a Roman numeral of 2. Let me just identify where that iron is, and you're going to see that iron is right over here. Okay, so nothing about its location on the periodic table hints to how many valence electrons it has. These B's over here are mute points. They do not tell you how many valence electrons they are, so we can actually just more or less scratch them out. They are useless information. But the Roman numeral you see at the by the name has an enormous purpose. And what that does is it tells us how many valence electrons it is. So if you have an atom of iron 4, where it shows the Roman numeral 4, it means that that iron has 4 valence electrons. So I would write my chemical symbol, and I would draw 4 valence electrons. That is iron 4. Now, as I said, transition metals can come in a variety of valence electrons. In some parts in the world, iron comes as iron 2. You'll see that this is a Roman numeral of 2, in which case this iron only exposes 2 of its electrons. All right? So next we have copper 1. before I answer it on my sketch pad, envision what copper 1 is going to look like as a dot diagram. If you guessed this, you're absolutely correct. That Roman numeral 1 tells me how many valence electrons it has. And then we have lead 2. So just lead is an unusual one. Its chemical symbol is Pb. And because of that Roman numeral 2, it tells us we have 2 valence electrons. So this is going to greatly help us when we work through ionic bonds. Remember, transition metals use Roman numerals to describe the valence electrons. So let's give it a try. Here I have iron 4 combining with oxygen. All right, so when we look at iron 4, we see the Roman numeral of 4. That tells us how many valence electrons we have. So I know that I have 4 valence electrons. I am going to draw iron with 4 valence electrons. Remember, make sure that you have a valence electron in each region before you start pairing them up. Next comes oxygen. So we will look at our periodic table. I'll go ahead and move back to our periodic table. We have oxygen right here at number 8. We know that it has 6 valence electrons. We know that thanks to the 6A. And so we know that oxygen is going to be surrounded by 6 dots. So we start with 1 dot in the north, 1 dot in the east, 1 in the south, 1 in the west, and now I start pairing them up. So we ask ourselves in this situation, is it easier for oxygen to gain 2 electrons or to lose 6? And the answer is gaining 2 electrons is a lot easier. Now for iron, we know that metals will lose electrons. In this case, you might ask yourself, well, 4 electrons, it can go either way, but metals will always lose the electrons. So at this point, iron wants to lose 4 electrons, but oxygen only wants to gain 2. How are we going to make sure that all of these atoms are going to reach noble gas configuration? Well, iron can donate 1 electron to the oxygen and 1 more electron. There we go. This oxygen has reached noble gas configuration. It has reached nirvana. But this iron has not. But if we give it 1 more oxygen, remember oxygen is only happy to gain 2 electrons. That works out perfectly. We have 1 electron going from the iron and then the last electron as well. And this allows that oxygen to now have a full valence shell. So next thing is writing the chemical formula. So your chemical formula remember is a series of symbols with subscripts. So I simply write iron with oxygen and a subscript 2. Keep in mind chemical formulas just tell you the type of element and how many you have of each. Notice I have no 4 in here anywhere. I'm simply counting how many elements I have and writing subscripts for if I have more than 1. How about the chemical name? Now the chemical name is a little different than our regular names. And in this one, you do want to write down what the Roman numeral is. So I would call this iron with parentheses 4 oxide. So for the chemical name, include Roman numeral. For this one, the chemical formula, do not, as you can imagine, there are many people who do not include Roman numeral. This one, the chemical formula, is simply a count of how many you have of each item or each element. So let's try one more of those. I have copper 1 combining with oxygen. What is its chemical formula? So we'll start with copper 1. Because of that Roman numeral 1, I know that copper has 1 valence electron. And we'll go back to our oxygen. We know that oxygen has 6 valence electrons. All right, same as what we've done before. We know that 1 copper will lose its electron. And so that copper has reached noble gas configuration, but the oxygen hasn't. So we're going to be adding 1 more copper. And it will lose its electron so that now oxygen has a full valence shell. Same thing that we've done before. We're going to write the chemical formula. And the chemical formula is copper. And how many coppers do we have? Copper 2. And then an oxygen, just 1. Notice I did not write the Roman numeral anywhere. Nowhere around copper do you see the number 1. The reason is the chemical formula is just counting how many you have of each of these elements. Now the chemical name. For the chemical name, I do want to include the Roman numeral. And the way I do it is I call it copper 1 oxide. Notice I am not writing copper 2. This Roman numeral does not tell me how many I have. It simply tells me how many valence electrons I have, okay? That's why it's copper 1, because it has 1 valence electrons. Do not write 2 here to identify that you have 2 coppers. That's done in the chemical formula. So now let's take a look at the other way around. So before I do that, when you are writing the chemical names, just remember you must include the Roman numerals, and they describe the number of valence electrons. So let's take a look at this one. What is the chemical name of FeCl2? Well, here you're in a situation where you know that Fe is a transition metal, but it doesn't tell you how many valence electrons it has. So the only way you can find out is by actually drawing it out. So let's start with what we know. And what we know is always or anion. We know that chlorine, without a doubt, has 7 valence electrons. And I know that because chlorine on my periodic table is number 17, and it is a halogen which all have 7 valence electrons. This chemical formula tells me I have 2 chlorines for every 1 iron. So let me draw those 2 chlorines. All right, and I have 1 iron. So what that is saying is that it took only 1 iron for chlorine, 2 chlorines, to get all their valence shells. So this chlorine wants 1 valence electron, I should say valence electron. So this chlorine needs 1 valence electron, and this chlorine needs 1 valence electron. That means combined, these chlorines need a total of 2 valence electrons, and that iron provided them with, just 1 iron provided them with both of that. So that means that this iron must have had 2 valence electrons, one that went to the first chlorine and the other one that went to the second chlorine. So knowing that iron has 2 valence electrons, I can now give it the chemical name of iron, and then it has 2 valence electrons. So I give it the Roman numeral 2, chloride. Remember, you always have an IDE ending. Okay, let's try one more. Here's another situation where we have a element or a ionic compound that has a chemical formula of Pb2O3. And when I look at Pb, it's number 82 on the periodic table, I see that it's in that transition metal region, which means that I cannot predict what the valence electrons are based on the periodic table. Instead, I need to recognize that it was 2 leads that were necessary to give oxygen, 3 oxygens, all of their electrons that they needed. So the first thing I like to do is start with the anion. So we know that we have 3 oxygens that are needed. Remember that each of these oxygens has 6 valence electrons when they start. Okay, so this is without question. Anions are always predictable because we always find them in the periodic table in a predictable region. Now this number 2 tells me that it took 2 leads to supply all the oxygens with the valence electrons that they needed. So let's count how many valence electrons these oxygens needed total. This oxygen needs 2 more valence electrons, so that's 2. This one needs 2 more valence electrons, so now 2 plus 2 equals 4. This oxygen needs another 2. So in total, all three of these oxygens need a total of 6 electrons. It is 2 leads that can provide 6 electrons. So if you have 2 leads, how many electrons do those leads have so that they can provide 6 electrons total? And the answer is 3. So if this lead has 3 and this lead has 3, that means that these leads have 6 electrons that they can give to the oxygen. And so we have 1 electron moving to this oxygen, another 1 electron moving there. We have an electron moving here to the second oxygen. The second lead is offering its first electron to the second oxygen. And voila. All of the leads have lost their electrons, and all the oxygens have gained 8 valence electrons. So now this lead here would actually have the name of lead 3 oxide. As you can imagine, a lot of people want to write down lead 2 thinking this number 2 should be represented as the Roman numeral. Remember, those valence electrons are represented by the Roman numeral. So this is actually lead 3 because it required lead with 3 valence electrons to supply all the electrons to oxygen. So yet again, I want to just reiterate, Roman numerals identify the number of valence electrons.